So thank you for this very nice introduction. And thanks for the organizers for inviting me. So yeah, I'm going to give two talks about about applications of zero knowledge proofs. So this first talk is on zero knowledge proofs for secure and private machine learning. So let me tell you what's the agenda so that I can set some expectations. So I will first start by discussing what is the problem of security for machine learning inference, how we can use zero knowledge proofs to solve this problem. But this is going to be a very quick part of the talk, and then I will dive into the more interesting problem, which is what are the challenges in constructing zero knowledge proofs for this problem that relate to efficiency, and in particular, I will focus on the case of neural networks, and that's why it's involved. So most of the talk will be about this, and I will have essentially one slide about the case of decision trees, and I will jump to book. Okay, so this is the motivation. So the motivation is outsourcing machine learning. So in this problem, we have mainly two parties. There is this client on the right side and some authority. And the idea is that the client has some data and he wants the data to be classified under some model, right? So now the model is owned by this authority. And so the authority runs some algorithm that is denoted by this function f, and is classifying. So it's coming up with an output y, which is this classification based on the machine learning model. And this is a problem that happens in this kind of paradigm that happens in several practical scenarios. For example, in banking and finance, you may use machine learning models in order to decide whether you can have a loan. What in terms of, let's say, coming up with a risk score that depends on your credit history, or you can use it in healthcare because you can train models to analyze medical images and or results of questionnaire and decide whether what's your risk of having a disease. And there have been even proposals, like there's some work by Shafi Golbasser that, for example, mentions how to even use it in the for criminal justice. Like you can have whether everything is ethical or not. It's a different question, and I'm not going to enter into this debate. But essentially, machine learning is there. Society is gonna adopt it somehow, and the question is that if we are using machine learning for such sensible application scenarios that involve our life, what about security? Right? So, and in particular, when we talk about security, the question is, we are on this side, we are the clients, and we get these results. We are not computing these results, and the question is, can we trust? Can we trust this classification outcome Y? And what does it mean to trust? First goal they would like is integrity. So we would like to detect if this computation is being tampered with, right? So if this authority, this server is not computing the function f that is supposed to. Now there is also a question of fairness because, assume that somehow the model is trusted, okay? So that you can trust that this model has been trained well. Can you ensure that this decision process is applied in a fair way to all users? It's me comes and I get this result Y, and it's computed according to model 1. Then someone else comes and it's maybe of a different gender, different race, and the bank is deciding to use a different model. How can you make sure this is not happening? And it's not an easy problem to even define, in terms of solutions, because usually in these settings, there is a privacy requirement in which these authorities don't want to reveal the models, right? These models are very, it's a confidential information. They invest a lot of money to train model, and also they use private data to train them, so they cannot just release them on the public so that someone can check that you're applying the same model. So for now, these goals are, vaguely explained. But when I'll describe the solution, it will be more clear how we can cryptographically define these properties. Now, one thing is that in order to resolve this privacy issue, and in the solution, we'll introduce some trusted parties. So, and these trusted parties is a part that's supposed to analyze the model, right? So in some sense, it should say, okay, look, this model is somehow good for some definition of good, and it will communicate this to the client. Okay, so in some sense, it's we have to, if we don't want the client to see the model, we have to introduce some party that does this. Okay, so
possibility result, or is just an easy way to go through that NPC cannot help with, or any transparency and so on.
I mean, let's put that this is a simplifying assumption for now. We can relax this assumption in the sense that maybe like you can have, I mean, if you can define a notion of goodness for the model, and we will actually see this at the very end of the talk, like you can replace this with some other proof. Okay. But you have to define, the problem is that how you define that the model is good. So, I mean, okay, maybe to give a spoiler, the idea is that, okay, maybe a definition of a model is good is that if you can trust some training data, then you can prove that the model has been trained correctly according to the data. But you have to trust that someone is not injecting fake data. And this is, then at that point, then you have to make some trust assumption. Okay, so first thing I want to discuss is how can we use zero-knowledge proofs to solve this problem, and in particular, we will also need commitment schemes. And this is going to be something very simple to state. So I'm not going to recall the definition of zero-knowledge proofs. Hopefully, you had enough during these days. I mean, I have a definition for commitments, but you also saw it in several talks. But I'll be very quick. So I'll mostly work here with the notion of non-interactive commitment. So this is a cryptographic primitive that essentially allows to commit to some value x, right? So the idea is that you put x in the box, and this is a process that you can formalize as an algorithm that takes this x and some randomness Rx and produces the commitment. And then in a second phase, you open the commitment with the idea that you reveal Rx, which acts like like a proof, and you can check that the commitment is computed correctly. And what you want from commitment schemes is that they are hiding, in the sense that if you commit to X or you commit to X prime, you cannot tell this apart. If you only see the commitment, so that is that the distribution of the commitment output is indistinguishable. And then there is binding that says that you cannot explain the same commitment with to two different inputs x and x prime. See? All right. So how can now we use commitments and zero-knowledge proofs for this setting? So the idea is that there is a commit phase, and in the commit phase now we are saying that this authority is committing to the model and is giving the commitment to the client. Okay, so that's essentially the let's say trust assumption we're making. Like this authority is expecting the model, says okay, it's good, and then it gives this commitment to the model to the client. So yeah, this is acting like a pointer, and we're gonna see why this is important. So once the client has the commitment, when you give the outcome of this classification, the idea is that you add a zero-knowledge proof that says, okay, look, this y is f of x w, and w is the same w that is in the commitment. And then you simply verify this zero-knowledge proof, right? So the statement of the zero-knowledge proof is x, the input, the output, and the commitment to the witness, which is the model, and then there is this proof. And yeah, I mean, I wrote everything as a non-interactive proof, but it could be also an interactive one.
So this would be like the commitment is to the kind of a computation, basically?
No, because, okay, right. So we'll see an example.
Can we think of the model as a zero?
Right. So the idea of model, usually what most of these algorithms, models are parameters of an algorithm, right? So if we're gonna see is like models are, for example, weights of some inner product computation. So the algorithm itself is f is public. So there is nothing special like about the algorithm. What is secret are the parameters of the algorithm. okay, why this gives us what we want? Essentially, integrity is implied by the fact that this knowledge proof is sound and the commitment is binding. I'm not gonna see the proof, but it's very intuitive. Privacy comes from the fact that the commitment is hiding, right? So the client here is receiving a commitment to the model, but this reveals no information about the model. And then the fact that the zero knowledge proof is zero knowledge, right, is not revealing any information about the witness, which is the model. Of course, you are leaking the outcome of the classification, but this is inherent in the functionality we want to achieve. Now, for you to know, there are other issues about reverse engineering, like models by looking at the outcomes, but this is not something that we are solving here. I mean, if you want, there are, for example, differential privacy techniques that wants to solve this. You could prove the differentially private algorithm in theory in zero knowledge. So about fairness, the idea, I mean, I will give an idea of fairness in terms of like, a proof by contradiction. So let's say that now there is another client that comes, and this client has the same commitment as the first client, right? So it has a commitment to W, and it wants to have X prime classified. So then there is a malicious authority that is classifying X prime using a different model W prime. Then, since this the protocol requires to produce a zero knowledge proof that must be accepted, then the this proof essentially should say something like this. So it should say that Y prime is a f of X prime W prime, and W prime opens the commitment. But we know that the zero knowledge proof is sound and commitment is binding, so you cannot open the commitment to a different W prime. Or if you you open the commitment to the same W, then you have to cheat in this part, in this branch of the proof.
Yeah. Seems kind of very similar to the integrity property.
Yeah, indeed. Like this fairness, I think is more like, if you talk about to machine learning people, like there is kind of this definition of fairness, but cryptographically, it's perfectly implied by integrity. The only thing is that it's implied by integrity when you introduce this model where there is this commitment. The point is that in real, like without the cryptographic solution, the commitment is not there, so it's not even clear you can define fairness. All right, so that's our solution, right? So that's our very generic and theoretical solution. Now, what I want to discuss is how we can construct proofs for machine learning algorithms. And what is the challenge? So the challenge essentially relates to scalability. Why? Because these models are very large, and the computations they involve are not very friendly with ZK proof techniques. So in particular, for example, if you think of neural networks of decision trees, to give you some ideas, like for example, there is a very famous neural network model which is called VGG16, which is a computer vision model for classifying images, and the size of the parameters of this model are 500 megabytes. So it means that you would have to process like you to do a zero knowledge proof that process 500 megabytes of inputs. And also in terms of operations, for example, neural networks, as we are going to see, have very dense matrix operations that involve the inputs. So it means matrix multiplication with parameters of that size. And also there are some nonlinear layers in which you have to perform operations that are not very friendly with zero knowledge proofs. And for example, if you instead think of decision trees, like that kind of computation is very non-algebraic. So it's about doing comparison with thresholds and moving along the nodes of a tree. So again, it's not, if you think of writing this as now an algorithm to a general purpose zero knowledge proof, it's very challenging. So, okay, when we talk about scalability, there could be two aspects to analyze. One is that of proof verification, but this is not very problematic, at least if we have snarks, right? Because if you have seen that snarks have this succinctness property, then you just throw a snark there, and you will solve the life for the verifier. But then when you throw a snark, then you have to think what happens to the prover. So this poor authority that has to, now is required to compute a proof, it has to compute a proof for this complex algorithm. And this is the most challenging problem that we're going to see. Ideally, what we would like is that the cost of proof generation should be as close as possible to the cost of running the inference algorithm. So ideally, would like some linear time prover, but really concretely with some very small concrete overhead. Right, because if the algorithm is already expensive by itself, we would like to optimize this. And the solution that we are going to see is how to use special purpose zero knowledge proofs instead of general purpose ones. Okay, so let me now dive into the case of neural networks, in particular these of convolutional neural networks. So a convolutional neural network is a computation that works like this. So it's a very sequential computation in which you start with your input X that you want to classify. Your model is actually, you can think of a collection of mini models, one per layer. And what you do is that you have a sequence of layer functions, F1, FL. And what you do is to take the input, to take this part of the model, and then you obtain some intermediate input X1. So you transform it and you obtain X1. And then you repeat the process with another layer function, and so on and so forth, until you get some last output YL, and that's your classification. Now, these layer functions don't have to be always the same, but essentially you kind of alternate a few of them. Now let's zoom in. What is a layer function in a convolutional neural network? And so for a layer K, what do you do is that you take this intermediate input XK and this witness or model WK. And what you do is to compute a convolutional layer or a fully connected layer. And this is a computation that is linear in XK, but it's very data intensive. As we're going to see, is like, really kind of touches all the inputs. And then you do a collection of kind of local functions that are called activation functions and pooling. So activation functions are, the most popular one is this ReLU function, which takes the max between X and 0, like in from essentially every entry of the input. And then pooling is a dimension reduction operation. So essentially, think of it that you get this the output from the previous function, you divide it in chunks, and then for every chunk, you kind of take a representative. And this representative can be taken with the average function or with a max function. So essentially, what you get here is like something smaller in dimension than what you had before. And then you iterate this, right? Okay, so what I'm going to present is how to construct zero-knowledge proofs for these convolutional neural networks using an approach that is based on sum-check-based proofs. So you have seen the GKR protocol and the sum-check protocol, I think, on the first day. So I'm going to show you how we can kind of rely on these techniques to do efficient proofs for CNNs. Why this? Like, one can wonder why this kind of approach. And one reason is that they are very suitable for this layered computation. So if you remember, the GKR protocol is a protocol that it takes a circuit and it proceeds layer by layer. Another reason is that they are efficient for the reason that when you look at the way these protocols work for proof generation, essentially most of the work is information theoretic. So you don't do any cryptographic work when you go across the layers, and you do only cryptographic work that is linear in the input of the computation. So in X and in W, but not, for example, in the trace of the computation. And I'm going to show you why this is the case. And this approach of using sum-check is mainly come from two works. The first work that introduced this idea is a work called ZK-CNN by Liu, Xi, and Zhang. And then there is a more recent work in which we kind of generalize this approach with David Balbás, Maribel González Vasco, Damián Robissu, and Claudio Soriente. And this is what I'm going to focus on. Okay, so and the way I'm going to describe the solution is with some modular approach. Okay, so the modular approach consists of the following steps. So the first step is something that we rely comes from some previous work, which is the idea that if you wanna create a snark for this relation, like something like y is f of x w, and you have a commitment to w, you can realize it by first creating an interactive proof for for this computation y is f of x w, and think of it of x w to be the input of the interactive proof, and then you add a polynomial commitment. So there is a compiler that takes care of this, and then you get an interactive, succinct interactive argument, then you can use Fiat Shamir to make it non-interactive. And I'll give an idea of how this works. So this was first formalized in a paper called VSQL. Okay, then what is more the newer part of our work is a way to construct interactive proofs by the combination of a new primitive that we call verifiable evaluation schemes, that you can think of simpler interactive proofs for subroutines that you can compose in order to build a full-fledged interactive proof for the composition of this function. So in the sense that like you have verifiable evaluation schemes for example, F1 and FL, and then you can generically compose them to build an interactive proof for some function which is a composition of F1, FL. So this is essentially a new framework for designing interactive proofs. And then once you have this framework, the nice thing is that, okay, now you can just focus on building verifiable evaluation schemes for example, the subroutines of a neural network. And if you think how these convolutional neural networks work, essentially you have to, for example, build a verifiable evaluation scheme for the convolutional layer, one for the activation function, and so on and so forth. Essentially, this is a kind of modular design and composition generalization of GKR style interactive. And I think this is, it's something that I like from my work, and I would like to convey and to explain. And what's the effect is that once you have this framework, you can kind of focus on designing schemes for specific functionalities. And in fact, for example, in our case, I think it helped us to focus on this convolution. We came up with new ideas to and more efficient ways to model the convolution operation. Okay, so let's see how we're doing with. Okay, so I have until 10, right? Okay, so let me recall what is an interactive proof very briefly. So this is a protocol between a prover and a verifier. I'm considering an interactive proof for a polynomial time computation y equals f of x, right? So where the verifier has everything as f, x, and y, and the prover is the same. So it's an interactive protocol that is supposed to be complete and sound. Okay, so then another object that I'm going to introduce is a kind of a new notion that we call fingerprinting. So fingerprinting of a data X with some randomness R, you can think of it as, some function H computed on XR, so some sort of hashing that is compressing. So the result is much smaller than X. And it is statistically binding in the sense that, over the randomness R, over the random choice of R, you cannot find two distinct X and X star that map to, that essentially hash to the same value. So it's a sort of hash function, but it's with respect to a random key. I mean, it's very close to the notion of universal one-way hash function in cryptography. And here is a very simple way to realize this. If you remember the lecture on the first day, which is by using multilinear extension. So if you have a vector X, the hashing of X with R consists into computing the multilinear extension of X, right? This polynomial X tilde that is multilinear, and to evaluate X on a random point R that is, of log n entries over a finite field. And why this is statistically binding? Because if you can find two inputs, so meaning two multilinear polynomials that over random R map to the same value, then by the Schwarzschild lemma, this is negligible if you work over a large field. Okay, so how can we use now this notion? So essentially the idea we started from was an observation that essentially most of the common interactive proofs follow the following structure. So they are, okay, and we are considering public coin interactive proofs. So they start with the verifier sampling a random RY. Then prover and verifier compute an output fingerprint of the, so a fingerprint of the output. And then they start a protocol where the verifier only knows the output fingerprint and its randomness, but it doesn't need to know X, and it does not need to know the output. And then, like at the very end, this protocol returns some candidate values CX, some value RX. So these are kind of computed jointly between prover and verifier inside the protocol. And then the protocol concludes by the verifier checking the bit B that this protocol is returning. So this the acceptance bit of the verifier in the V's part. And then you check the input fingerprint. Right. So essentially this structure is really there in many interactive proofs. And what is interesting about this is that this protocol here works without the verifier needing to know inputs and outputs. It only needs to know these succinct fingerprints. And examples of this structure are the sum-check protocol, as I'm going to show, and the GKR protocol as well, and other protocols that exist in the literature.
I don't understand, why does the prover and the verifier have exactly the same input? Couldn't the verifier not know X, for instance?
We're not talking about like zero knowledge here. This is really like interactive proofs. Like you want to check that the circuit is evaluation is correct, and you want to do it faster than F. I mean, for having succinctness, you have to, I mean, if you remember GKR, you have to assume that probably this F has some short representation, right? So for example, the wiring of F must be represented with small polynomials. Okay, so one interesting aspect before going to the example is that we can define a soundness notion for this subroutine, right? So what does it mean that this subroutine is sound? And the idea of, the way we define soundness of a verifiable evaluation scheme is that is to say that for random Rx and Ry and any unbounded adversary A, it is essentially, what we want to evaluate is the probability that an adversarially generated output fingerprint C star Y is not the fingerprint of f of x when you accept in this proof, right? So essentially here we're saying, consider an adversary that chooses at the very beginning an adversarial C star Y, and you run the V protocol, right? And then you check correctly the input fingerprint. Then you want to make sure that this is an hash of f of x. So in simpler terms, what we want is that if you check correctly the input fingerprint, the output fingerprint must be correct on f of x. Okay, so and the idea is that with this soundness notion, we can show that the soundness of this subroutine in purple here plus the binding of the fingerprint, we can show that then that full-fledged protocol where you add the first round and this last check is a sound interactive proof. Okay, so now I want to give you the example, like why this is a a good notion set how we can capture existing protocols. So let's look at the sum-check protocol. So if you remember, the sum-check protocol is a protocol where the prover has a multilinear polynomial x that in L variables, and he wants to convince the verifier that y is the sum check of x. So essentially, it's this function that is computing x on all the elements of this L-dimensional hypercube. And okay, so sorry, the verifier has access to X as well, because, or Oracle access to it. So in the very fast, essentially the sum check protocol proceeds by having the prover sending these univariate polynomials in L rounds, and it concludes by the verifier checking something for every pair of consecutive polynomials. So this kind of equation fi of 0 plus fi of 1 must be equal to fi minus 1 of some randomness I minus 1. And then you check that the last polynomial, univariate polynomial, is equal to x evaluated on R1, RL, and you evaluate this on RL. So here I'm just writing the sum check protocol. And the reason why this is a verifiable evaluation scheme is because we can do a very trivial transformation where we can think that instead of locally sampling RL, actually RL is sent to the prover, and the prover returns CX as a candidate, and that for now you don't know if it's correct or not. And then you can think that this is actually the V execution where the prover and verifier get CX and RX, and RX is R1, RL, right? All the randomness is jointly, the random challenge is chosen by the verifier. And then what you do is that instead of checking this, you first kind of check FL against the candidate CX, and then you check that CX is, the evaluation of X. I mean, I'm just rewriting everything, right? But once you move this, then you can think that this is a V protocol. You are checking a fingerprint of the input. And if you wonder where there is a fingerprint of the output, it's actually there because like the output is a scalar value. And if you do a multi-linear extension of a scalar value, you have identity function, right? So, in some sense, there is a trivial RY that you're sending, and that's what is CY. Okay, so, and what about GKR? I mean, I'll be very fast because otherwise I don't have time to cover the rest. But essentially, you can think that GKR also starts by computing a fingerprint of the output with a random RY, and then you start a sum check claim about this fingerprint of the output to the right, and then this is converted into some other sum check claims about the intermediate layers, and it concludes with some claim about the fingerprint of the output of the first layer that you check against the input, the multi-linear extension of the input. But again, we can rewrite this as a VE protocol where essentially you conclude by checking an input fingerprint. And what is interesting, again, like in GKR, like the verifier doesn't need to know the inputs and outputs in this middle protocol. And you can do the same abstraction even for the subroutines of GKR, right? So, okay, so what can you do once we have this abstraction of evaluation scheme? So is that we can have a generic composition theorem that says, assume that you have a verifiable evaluation scheme for function F1, and another one for function F2 that is of the form, for example, F2 of ZW, then you can build a verifiable evaluation for the sequential composition of these two functions, right? So something like F of XW is F2 of F1 of XW. And I'm giving you a simplified example of how we can construct this composition. So assume that instead of having this kind of nesting, you have a more purely sequential composition of F1, F2, F3. So it's like, you compute Y as F1 of F2 of F3 of X. And the way you build a V for this function F from V's for the subroutines is by doing the following. So in the interactive proof, you would send first the RY, right? Then the first thing you do is that they compute an output fingerprint, and they start the V for function F3. So you start from the output, right? This returns fingerprints for the intermediate input, right? So for this in fingerprints of X2. But then the verifier at this point is not gonna, it doesn't know X2, right? So what it does is then you recurse and then say, okay, let me now check that C2 is actually a fingerprint of the correct intermediate layer, and you launch a V for F2, and then again you do the same for F1. And then the idea is that the first V execution tells you that under the assumption that C2 is a fingerprint of X2, then CY is a fingerprint of F3 of X2. And then you say, okay, like, how can I check that C2 is correct? And that's your second execution that tells you, okay, like, if C1 is a fingerprint of X1 for some X1, then C2 is a fingerprint of F2 of X1. And then you repeat the other one, and then essentially, like, you get that by composition, if this is a fingerprint of the input, then CY must be a fingerprint of the composition of this function.
Why is it okay to think the intermediate C1, C2? Because it's not randomized, right?
Right. Okay. For now, we are not considering zero knowledge. Yes. That's a good question. So what is interesting here is that you have to think that all these fingerprints are short, right? So the communication of this composition is still short. That does not depend on the size of the inputs or the size of the intermediate layers. Okay, so then how can we now use a verifiable evaluation scheme in order to get a snark? I'm giving a simplified version of this compiler for the case where you can think that there is no W. In some sense, X is your witness, okay? You want to prove that something like this, Y is f of X, and you have a commitment to X. So the idea is that you take the verifiable evaluation. So this comes from this VSQL paper. So the idea is that you execute the verifiable evaluation scheme for F, and you plug it as an interactive proof. So where there is this output fingerprinting at the very beginning. And then you simply add a proof. So you need a tool, which is a snark for this simpler language. Let's say that essentially it's the language that proves that CX is a fingerprint of X under some randomness Rx, and X is committed. And then the idea is that it's very simple, like, you execute the V's. Now the verifier does not have X. He only has a commitment to X, and then you use this proof to convince the verifier that it would accept in the V protocol. Is this clear? And the nice thing is that when this fingerprinting function is this multilinear polynomial evaluation, that yellow object is multilinear polynomial commitment. So it's not like a fancy snark. So it's really this very simple object.
Because you're not using a hash function.
There is no hash. The hash function is computing the polynomial evaluation. Okay. What about zero knowledge? I'll give hints because, like, for sake of time, I prefer to focus on succinctness. But the idea is that if now this commitment is an hiding commitment, you don't reveal anything about the input in the commitment, right? And then you need some, you also need the zero knowledge of this PyH system so that this proof here does not leak information on what is committed. But then you need some zero knowledge on the interactive rules. You have to make sure that this purple protocol here does not leak information on X. So there are two approaches to do this. One approach is essentially to execute a committed version of this protocol. So this was, for example, proposed in two works, in IRAX and zk-VSQL. This is a bit of expensive because then you have to kind of throw commitments and some simple zero knowledge proofs in this execution of the protocol. So you would lose this advantage that this protocol is all information theoretic. Or there are like randomization techniques that to make the sum check protocol zero knowledge, that essentially you kind of get a zero knowledge version of the interactive proof. So you can kind of randomize the interactive proof so that the transcript, and in particular these fingerprints that you leak, are randomized enough to not leak information on the input. Okay. Okay.
Go 5-10 minutes.
Okay. Yeah. Okay, so let me just focus now on again, we're going back to neural networks and in particular on this convolution operation. So what is convolution? So essentially convolution is an operation that takes an input X, which is an n times n matrix, and the kernel W that is also a matrix of size m times m. Typically, m is much smaller than n. And then you compute the output according to this formula. And I'll give you a very simple description of this formula, which is what you do is that you take a submatrix of X of the same size of the kernel, and then you compute an inner product of the vectorization of these matrices. Okay, so what you're doing is that is an inner product of this times this plus this times this and so on. And then you send it, for example, here you send it on the top left entry of the output. And then, you slide your window and you send the result on the other entry of the output. So this is essentially a two-dimensional convolution.
Why is it called kernel?
I don't know.
Kernel of something.
No, I don't know. I should ask ML people. Okay, in a convolutional neural network, in that kind of what happens is that you have actually what are called multiple channels. So in the sense the input is not one matrix. So for every layer, you have several matrices. So you have C of K matrices for every layer. So for example, for the input layer, if you're working with images, you would have three matrices, one for red, one for green, one for blue, right? So you're like what these channel is like essentially is a way to encode multidimensional data. And the same then for the kernels, what you have is that, so okay, what happens is in multi-channel convolutional neural network is that you have this input, which has, let's say, C channels, and then you have an output that has another number of channels. Let's say it has these channels, in this precisely it has C of K plus one channel. So for every layer, you have different dimensions. And then these kernels, you actually have kernels for every sigma tau pair. So, for you have one for essentially, if you have CK and CK plus one output channels, you have CK times CK plus one kernel metric. And this is what you compute. So it's like, for one output channel, you compute the convolution operation that I had in the previous slide. Okay, so now essentially, now this means that what we want to prove is this kind of operation. And the observation is that if you want to write this as a circuit, it can be very expensive. So it is a circuit that it has size that depends on is like multiplication of input channel, output channel, size of the kernels, like, of each kernel, and size of the output. And the output is roughly the size of the input. I mean, it's, I didn't show it, I didn't post, but essentially the dimension of the output is a dimension of the input minus dimension of the kernel plus one. Okay, and the idea is to use some special purpose techniques, and there are, I'm going to mention two approaches in which the idea is to express convolution as a structure matrix multiplication. So in particular, in ZK-CNN, what they did is this kind of transformation. So they encoded this two-dimensional convolution with a one-dimensional convolution that actually can be expressed as a polynomial multiplication. And then they prove polynomial multiplication using FFT algorithms, and they have a way to encode, to prove FFT multiplications, so FFT-based polynomial multiplication using matrix multiplication. What we did in our work was a different kind of encoding. We kind of, I'm going to show it. So it's a reshaping idea so that we can encoding with the matrix multiplication. So, right, what's the idea? So essentially the idea is that if you want to compute convolution of X and W, you can express it as the multiplication of this matrix, which is like X with some redundancy. In every row of this matrix, you essentially you put the vectorization of the submatrix that you want to consider. For example, here you take X0, X1, X3, X4, which is the top left submatrix of dimension 2, and then you proceed. So you have essentially now a matrix of whose number of columns is the dimension of the kernels squared, right? So it's m squared, and then in the number of rows is the output dimension. And then now you can see this as a matrix vector multiplication, but then we have to formalize this for channels and for multiple channels, and where it is interesting in the sense that what we do is that you first reshape each single matrix, and then when you see what happens for every output, and you stack the vectorization of these outputs one after the other for the output channels, you can essentially express this as the sum of a matrix multiplication. So between the reshaping of the input and the reshaping of the kernel matrices, that according to this formula. So, I mean, with this essential idea that you can express V for convolution with a verifiable evaluation scheme for sum of matrix multiplications. Okay, so I think I'll focus on this because I think this is a very important result in the case of in the area of interactive proofs, and then I'll be very fast to conclusion. Okay, so to do a V for matrix multiplication, we essentially use a protocol that was proposed by Thaler in 2013. And it's a very influential protocol, I think, in the area of sum check-based proofs. So it's a way to do an interactive proof for C equals A times B, right? So where A, B, and C are n-dimensional matrices over a finite field. And with the property that like the running time of the prover is n squared, so it's linear in the size of these matrices, which is optimal if you think that even computing matrix multiplication cannot be done in complexity n squared, or it's not known to be doable with such a complexity. And then the communication and verification complexity of the V part is log n. I mean, the verifier, if he knows the matrix, must process the matrix in times n squared, but the proof is log n. Okay, so how does this work? So first of all, it relies on the following formula. So here we are computing multilinear extensions of the matrices. So now it's the multilinear extensions have two log n variables, and we are essentially saying that C tilde of ik encodes CIK, the entry CIK of the matrix, and this is essentially a rewriting of the matrix multiplication formula in multilinear extension form, right? So everybody with me on this? Okay, so what you do is to first compute a fingerprint of the output matrix C, and this consists into sampling two random vectors of log n sides R1 and R2. Prover and verifier computes the fingerprint, which consists into computing the multilinear extension of these output matrix on R1 and R2. And then what you want to do is to prove the following sum check claim. So you want to prove that this output fingerprint that I'm calling C with C is the sum check of a polynomial xj, which is the product of the A tilde on R1j and B tilde on J R2. Right, so in taking this, right, so this formula, and we are replacing I with R1 and K with R2. Right, so because we are evaluating now, we're thinking of these as multilinear polynomials, and we're essentially we're right. So this, you can, maybe it's better to think that this polynomial is the partial evaluation of the multilinear extension on R1, and this is of A on R1, and this is the partial evaluation of the multilinear extension of B on R2 on the second half of log n variables.
Is X then also again?
So X it doesn't need to be materialized, right? So it's precisely this is a sum check for the product of two polynomials. So it's enough to work with these two polynomials. You can simulate X by having access to the A tilde and B tilde. It's a good question. So I mean, there is a mismatch. Like precisely, you need to work with a variation of sum check. I don't know if you saw it in the first lecture, which works for product of polynomials. So you can generalize sum check in these cases.
I didn't quite get, so the prover time is faster than computing this product of the matrices. But when you really run this, the prover would still have to do the product, right?
Yes, yes,
Okay,
right.
okay,
Yeah,
got
yeah, no, right. This is assuming that, but essentially this means that you don't have to care in about when you do the proof how you compute the result. So if there is a complicated algorithm, you are using Strassen's algorithm to compute this matrix multiplication, you don't have to do a proof of Strassen algorithm. No, you just run your Strassen algorithm to do fast matrix multiplication, then you exploit the fact that you know the result to do the proof faster.
Because initially I was not sure if we then maybe can do this in n squared using some techniques from this, but I think this is not for computing, it's just for proving once the result is known.
Right, yeah, exactly. This is for computing the proof once you have the result, right? So, right, and then essentially you run a verifiable evaluation for the sum check to prove this claim. And then it concludes by checking the fingerprints of the input matrices, right? So that's the idea. So if essentially, since we are just running a sum check protocol here, the soundness relies on the sum check protocol soundness and the binding of this fingerprint, and so the fact that these multi extensions, you cannot find collision for them. Okay, so okay, I think now I'll go very fast. So essentially, this is what you get in terms of convolution after you apply this matrix multiplication protocol. Essentially, the cost for the prover is linear in number of input channels times the size of the kernel times the size of the output plus the number of output channels. And instead, for the case of ZK-CNN, with their approach, they were getting something like this. So it's a number of input channel times output channel times size of the input. We're not improving overall parameter regime, but like in practice, this size of the kernel is very small. You can think that M is free, like sometimes you use 3 times 3 matrices. And the number of output channels, for example, can go much larger. It depends on which layers you are, but can go up to 512. So that's why, for many realistic convolution, this is going to be asymptotically faster than the other one. And we confirm this experimentally. So, for example, we improve by 5 to 10 times compared to the previous one. Okay, so yeah, I will skip the decision tree part, but you will find in the slides that there are 2 main pointers on how to model decision tree with special purpose techniques. One uses essentially a Merkle tree-based technique to encode the decision trees and to prove, we're essentially proving inference corresponds to proving correct traversal of this tree. And in another work that we had at PKC 2024, like we said, use a matrix encoding of the decision tree that allows to reduce the problem of decision tree evaluations to proving lookups over this matrix. Okay, so in this talk, I try to discuss how to construct ZKP for the case of ML inference, in particular for convolutional neural networks. I want to mention very fast, like other related problems. One is that of proving accuracy. So which means once you have a model that, let's say, it's committed, how can you prove that this is a good model? It's an accurate model. And actually, it's possible to reuse an ML inference solution, because like you can take a public data set that is labeled and for which you know the correct classification, you can let the prover prove classification for this data set, and then the verifier can compare whether the results are accurate or not. And then a very active area of research right now is that of proof of training. So how can you prove that W is obtained from some data? So there are, I'm putting here references for 2 recent works that use different techniques to do this. For example, in this work that is going to appear at CCS 2024, actually uses inside also GKR-based techniques, but then in order to, the problem with training is that you iterate many times. So what they do is to use incrementally verifiable computation to deal with these iterations. And yeah, thanks for your attention, and I'll be happy to take more questions.